governments grew larger, it became necessary to find ways to administer them. Areas of land needed to be calculated, crop yields predicted, taxes charged and collated. In short, people needed to count and measure. The Egyptians used their bodies to measure the world, and it's how their units of measurement evolved. A palm was the width of a hand, a cubit an arm length from elbow to fingertips. Land cubits, strips of land measuring a cubit by 100, were used by the pharaoh's surveyors to calculate areas.
There's a very strong link between bureaucracy and the development
System, motivated by the 10 fingers on our hands. The sign for 1 was a stroke, 10 a heel bone, 100 a coil of rope, and 1,000 a lotus plant.
Yeah, how much is this T-shirt? 25. Yes. So that would be 2 knee bones and 5 strokes. Yes. So you're not going to charge me anything up here?
Here, 1 million.
1 million?
Oh my God.
No.
Is this 1 million?
1 million. Yeah, that's pretty big.
The hieroglyphs are beautiful, but the Egyptian number system was fundamentally flawed. They had no concept of a place value, so 1 stroke could only represent 1 unit, not 100 or 1,000. Although you can write 1,000,000 with just 1 character, rather than the 7 that we use, if you want to write 1,000,000 minus 1, then the poor old Egyptian scribe has got to write 9 strokes, 9 heel bones, 9 coils of rope, and so on, a total of 54 characters. Despite the drawback of this number system, the Egyptians were brilliant problem solvers. And many secrets perished with it. But there's one revealing document that has survived.
The Rhind mathematical papyrus is the most important document we have today for Egyptian mathematics. We get a good overview of what types of problems the Egyptians would have dealt with in their mathematics. We also get explicitly stated how multiplications and divisions were carried out.
The papyri show how to multiply 2 large numbers together. But to illustrate the method, let's take 2 smaller numbers. Let's do 3 times 6. The scribe would take the first number 3 and put it in one column. In the second column, he would place the number 1. Then he would double the numbers in each column. So 3 becomes 6, and 6 would become 12. And then in the second column, 1 would become 2, and 2 becomes 4. Now here's the really clever bit. The scribe wants to multiply 3 by 6. So he takes the powers of 2 in the second column, which add up to 6. So that's 2 plus 4. Then he moves back to the first column and just takes those rows corresponding to the 2 and the 4. So that's 6 and the 12. He adds those together to get the answer of 18. But for me, the most striking thing about this method is that the scribe has effectively written that second number in binary. 6 is 1 lot of 4, 1 lot of 2, and no units, which is 1, 1, 0. The Egyptians have understood the power of binary over 3,000 years before the mathematician and philosopher Leibniz would reveal their potential. Today, the whole technological world depends on the same principles that were used in ancient Egypt. Problems mention bread and beer, which isn't surprising, as Egyptian workers were paid in food and drink. One is concerned with how to divide 9 loaves equally between 10 people, without a fight breaking out. I've got 9 loaves of bread here. I'm going to take 5 of them and cut them into halves. Of course, 9 people could shave a 10th off their loaf and give the pile of crumbs to the 10th person. But the Egyptians developed a far more elegant solution. Take the next 4 and divide those into thirds. But 2 of the thirds I'm now going to cut into fifths, so each piece will be 1/15. Each person then gets 1/2 and 1/3 and 1/15. It's through such seemingly practical problems that we start to see a more abstract mathematics developing. Suddenly new numbers...
Vulcan.
According to legend, Horus's father was killed by his other son, Seth. Horus was determined to avenge the murder. During one particularly fierce battle, Seth ripped out Horus's eye, tore it up and scattered it over Egypt. But the gods were looking favourably on Horus. They gathered up the scattered pieces and reassembled the eye.
Each part of the eye represented a different fraction, each one half the fraction before. Although the original eye represented a whole unit, the reassembled eye is 1/64th short. Although the Egyptians stopped at 1/64, implicit in this picture is the possibility of adding more fractions, halving them each time, the sum getting closer and closer to 1, but never quite reaching it. This is the first hint of something called a geometric series, and it appears at a number of points in the Rhind papyrus. But the concept of infinite series would remain hidden until the mathematicians of Asia discovered it centuries later. By shapes that the Egyptians already understood. The Rhind papyrus states that a circular field with a diameter of 9 units is close in area to a square with sides of 8. But how would this relationship have been discovered? My favourite theory sees the answer in the ancient game of Mancala. Mancala boards were found carved on the roofs of temples. Each player starts with an equal number of stones, and the object of the game is to move them around the board, capturing your opponent's counters on the way.
As the players sat around waiting to make their next move, perhaps one of them realised that sometimes the balls fill the circular holes of the Mancala board in a rather nice way. He might have gone on to experiment with trying to make larger circles.
Perhaps he noticed that 64 stones, the square of 8, can be used to make a circle with diameter 9 stones. By rearranging the stones, the circle has been approximated by a square. And because the area of a circle is pi times the radius squared, the Egyptian calculation gives us the first accurate value for pi.
The area of the circle is 64. Divide this by the radius squared, in this case 4.5 squared, and you get a value for pi. So 64 divided by 4.5 squared is 3.16, just a little under 2/100ths away from its true value. But the really brilliant thing is the Egyptians are using these smaller shapes to capture the larger shape.
Called one of the 7 wonders of the ancient world. They're simply breathtaking. And how much more impressive they must have been in their day, when the sides were as smooth as glass, reflecting the desert sun.
To me, it looks like there might be mirror pyramids hiding underneath the desert, which will complete these shapes to make perfectly symmetrical octahedrons. Sometimes, in the shimmer of the desert's heat, you can almost see these shapes.
It's the hint of symmetry hidden inside these shapes that makes them so impressive for a mathematician. The pyramids are just a little short to create these perfect shapes. But some have suggested that another important mathematical concept might be hidden inside the proportions of the Great Pyramid: the golden ratio. 2 lengths are in the golden ratio if the relationship of the longest to the shortest is the same as the sum of the 2 to the longest side. Such a ratio has been associated with the... For me, the most impressive thing about the pyramids is the mathematical brilliance that went into making them, including the first inkling of one of the great theorems of the ancient world, Pythagoras' theorem.
In order to get perfect right-angled corners on their buildings and pyramids, the Egyptians would have used a rope with knots tied in it. At some point, the Egyptians realised that if they took a triangle with sides marked with 3 knots, 4 knots and 5 knots, it guaranteed them a perfect right angle. This is because 3 squared plus 4 squared is equal to 5 squared. So we've got a perfect Pythagorean triangle. In fact, any triangle whose sides satisfy this relationship will give me a 90-degree angle. but I'm pretty sure that the Egyptians hadn't got this sweeping generalization of their 3-4-5 triangle.
We would not expect numbers, and then if a verification would be carried out at the end, it would use the result and these concrete given numbers. There's no general proof within the Egyptian mathematical texts.
It would be some 2,000 years before the Greeks and Pythagoras would prove that all right-angled triangles share certain properties. This wasn't the only mathematical idea that the Egyptians would anticipate. In a 4,000-year-old document called the Moscow Papyrus, we find a formula for the volume of a pyramid with its peak sliced off, which shows the first hint of calculus at work.
For a culture like Egypt, that is famous for its pyramids,
to understand how they derive their formula, start with a pyramid built such that the highest point sits directly over one corner. 3 of these can be put together to make a rectangular box. So the volume of the skewed pyramid is 1/3 the volume of the box. That is, the height times the length times the width divided by 3.
Now comes an argument which shows the very first hints of the calculus at work, thousands of years before Gottfried Leibniz and Isaac Newton would come up with the theory.
Suppose you could cut the pyramid into slices. You could then slide the layers across to make the more symmetrical pyramid you see in Giza. However, the volume of the pyramid has not changed, despite the rearrangement of the layers. So the same formula works. The Egyptians were amazing innovators, and their ability to generate new mathematics was staggering. For me, they revealed the power of geometry and numbers, and made the first moves towards some of the exciting mathematical discoveries to come. But there was another civilization that had mathematics to rival that of Egypt, and we know much more about their achievements.